They had been studying Jupiter for 9 years. 9 years of close flybys, 9 years of images, 9 years of data from a spacecraft that had orbited the largest planet in the solar system more than 70 times, and sent back thousands of raw photographs of its cloud bands, its storms, its moons, and its poles. They thought they understood it. Not completely. Nobody who works in planetary science ever claims to understand Jupiter completely, but well enough to have firm expectations about what the next batch of data would show. And then the images came back from the 72nd Perigove, and the scientists at NASA's Jet Propulsion Laboratory looked at what the Juno spacecraft had captured during its closest approach on May 8, 2025. And the word that appeared most often in their responses was one they had been using with unusual frequency throughout the mission, more complicated than expected: Jupiter, the planet. Humanity has been watching through telescopes for 4 centuries. The planet Galileo first saw moons orbiting in 1610. The planet that ancient civilizations tracked across the sky and named for the king of their gods has turned out, under the close examination of the Juno mission, to be fundamentally different from everything the models predicted. Not in one way, not in 2 ways. In every way that matters: its magnetic field, its atmosphere, its interior, its polar regions, and the moons that orbit it. Each new batch of images, each new dataset transmitted back across 500 million miles of space, has forced researchers to revise assumptions that had stood unchallenged for decades. And in the final months of Juno's mission, with the spacecraft approaching the end of its life, making its last close passes of the planet that has defined its existence, what it has shown us is a world of staggering, almost defiant complexity, unlike anything the solar system was supposed to contain. The Juno spacecraft launched from Cape Canaveral on August 5, 2011, and arrived at Jupiter after a 5-year journey on July 4, 2016. It is the furthest solar-powered spacecraft ever flown. At Jupiter's distance from the Sun, sunlight is approximately 25 times weaker than it is at Earth. And Juno's 3 massive solar panel wings, each spanning nearly 9 meters, generate only about 500 watts of electricity in the Jovian environment. That is roughly the power consumption of 5 household light bulbs. The spacecraft that has been producing some of the most scientifically significant data in the history of planetary science runs on less electricity than it takes to power a modest kitchen appliance. Juno was designed for a specific mission: to peer beneath Jupiter's cloud tops and understand the planet's interior structure, its magnetic field, its atmospheric composition, and the origins of its powerful aurora. The spacecraft carries a suite of instruments including JunoCam, a 2-megapixel visible light imager whose raw images are released to the public for processing by citizen scientists, and more sensitive instruments including a microwave radiometer that can see deep into the atmosphere, a magnetometer, a gravity science instrument, and ultraviolet and infrared cameras designed to study Jupiter's auroras and the thermal emission from its cloud layers. What Juno found when it arrived at Jupiter in 2016 and began making its closest approaches, called perijoves, the Jovian equivalent of a spacecraft's closest point to any planetary body, forced a comprehensive revision of what planetary scientists thought they knew about gas giant planets. And what it has continued to find, right up through its most recent close passes in 2025, has confirmed that Jupiter is not simply more complex than expected, in the way that scientific subjects always reveal more nuance on closer inspection. It is fundamentally different in ways that challenge models of how planets form and how gas giant atmospheres work that had been accepted as established science for decades. The first and perhaps most fundamental of the Juno discoveries concerns Jupiter's magnetic field. Every planetary scientist knew that Jupiter had a powerful magnetic field. Its magnetosphere is the largest structure in the solar system, dwarfing even the Sun in sheer volume, extending millions of kilometers into space and creating an environment of intense radiation that makes Jupiter one of the most hostile destinations for spacecraft in the entire solar system. What the models predicted was that this field would be generated by the same mechanism as Earth's magnetic field: a rotating, conducting fluid core generating a dipole field with a north magnetic pole and a south magnetic pole, roughly aligned with the planet's rotation axis. What Juno's magnetometer found was nothing like that. Jupiter's magnetic field is not a dipole. It is an extraordinarily irregular, asymmetric, lumpy structure with multiple poles embedded in a pattern that is far more convoluted in the northern hemisphere than in the southern, as the Astronomy Picture of the Day summary from January 2026 described it. Jupiter's magnetic field has been discovered to be much different from Earth's simple dipole field, showing several poles embedded in a complicated network more convoluted in the north than the south. The field is so asymmetric that the southern hemisphere and the northern hemisphere appear to be operating under fundamentally different magnetic regimes, suggesting that the mechanism generating it is more complex and more spatially variable than any dynamo model had predicted. This finding has direct implications for how planetary scientists understand the interior of Jupiter. the hidden region below the cloud tops that no instrument has ever directly sampled. If the field is generated by a rotating conducting layer, the asymmetry and multipolar structure of what Juno measured suggests that layer is not uniformly distributed or uniformly conducting. It suggests patchiness, variability, a dynamo operating in conditions that the models did not anticipate. And understanding what those conditions are, what the interior of Jupiter actually looks like, how its metallic hydrogen layer is structured, whether it has a solid core or a diffuse one, is one of the central unsolved problems in planetary science that Juno was built to address. After 9 years, the answer is not settled. What Juno's magnetic data has produced is a much more detailed map of the mystery, rather than its resolution. The second major revelation from Juno's latest images and data concerns what is happening inside Jupiter's atmosphere specifically, how deep that atmosphere actually is, and how far down its structure extends. Jupiter's visible surface, the bands of cloud in yellow, white, orange, and brown that Juno's JunoCam has been photographing since 2016, was assumed to be relatively shallow. The distinctive banding, the jet streams, the storms, including the Great Red Spot, were expected to be features of the upper atmosphere, driven by solar heating and confined to a relatively thin outer layer of the planet's enormous bulk. Below some depth, the assumption went, the atmosphere would become uniform, the pressures and temperatures too high for the kind of differential chemistry and dynamics that drive the visible surface features to persist. Juno's microwave radiometer has systematically dismantled this assumption. Its radio measurements penetrate hundreds of kilometers below the visible cloud deck, sampling the atmosphere at depth in a way that no previous mission had achieved. What those measurements show is that Jupiter's atmospheric structure, the alternating bands of different chemical composition and wind speed, extends far deeper than expected. As the January 2026 Astronomy Picture of the Day summary noted, Juno's radio measurements show that Jupiter's atmosphere shows structure well below the upper cloud deck, even hundreds of kilometers deep. A major new study published in the Planetary Science Journal in January 2026, led by researchers at the University of Chicago and the Jet Propulsion Laboratory, produced what was described as the most detailed model of Jupiter's atmosphere ever created. The researchers tackled one of the most vexing open questions about Jupiter: how much water does it contain? Water is the key to understanding how Jupiter formed. It is a critical tracer of the conditions in the early solar system where the planet accreted, and it drives the chemistry that determines the cloud structure visible in the images Juno sends back. The new model, which coupled chemical kinetics with hydrodynamic simulations in a way that no previous model had attempted at this scale, concluded that Jupiter's oxygen abundance, the best proxy for its water content, was only 1 to 1.5 times the solar abundance, significantly lower than previous models had suggested. This has profound implications for theories of how Jupiter formed and what its building blocks were. The clouds, as Science Daily described it, are hiding something big, and what they are hiding has turned out to be different from what the models predicted. The polar images are where the Juno mission has produced its most immediately dramatic visual results, and where the gap between what the models expected and what the spacecraft found is most viscerally apparent. Before Juno, no spacecraft had ever made close observations of Jupiter's polar regions. The Voyager missions in 1979 flew past Jupiter on trajectories that allowed excellent views of the equatorial and mid-latitude regions, but not the poles. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, similarly had limited polar coverage. Juno was the first spacecraft specifically designed to orbit over the poles, dipping down on a highly elliptical path that brought it close to Jupiter at every perijove, before swinging back out to a great distance. And when those first polar images came back in 2016, the scientists looking at them described an experience of genuine shock. Every other large planet in the solar system with a well-understood polar region, Saturn, Neptune, even Earth has a polar vortex. A single large cyclonic circulation at or near each pole driven by the planets. Rotation, models of Jupiter's atmosphere based on what we knew about gas giant dynamics predicted the same. One cyclone at the North Pole, one at the South Pole, well organized, well understood. What Juno found was 9 cyclones at Jupiter's North Pole arranged in a regular octagonal pattern around a central cyclone, 8 circling 1, and at the South Pole, 6 cyclones in a pentagonal arrangement around another central cyclone, 5 circling 1. Not one cyclone, not 2, a geometrically organized cluster of massive atmospheric vortices, each one comparable in size to entire countries or small continents arranged in regular polygonal formations that persist year after year without merging, without destabilizing, without the central cyclone absorbing the surrounding ones, the way that atmospheric physics on every other planetary body studied would predict. Subsequent observations have confirmed that these polar cyclone clusters are stable, they persist, they maintain their polygonal arrangement, and they do not behave like anything in the existing models of planetary atmospheric dynamics. The images of these cyclones, rendered in false color by both NASA scientists and citizen scientists processing JunoCam's raw data, are some of the most striking photographs ever taken of another planet. They look, in the words of more than one researcher, who first saw them, like nothing in the solar system should look like. Massive swirling systems of cloud and storm, each one large enough to contain multiple Earths organized in patterns that would look more at home in a geometry textbook than in an atmospheric science paper. The third major area of stunning results from Juno's latest mission phase concerns not Jupiter itself, but its volcanic moon Io, and what it has revealed about Io's extraordinary and still partially mysterious internal dynamics. Io is the most volcanically active body in the solar system. This has been known since Voyager 1 captured the first images of active volcanic plumes rising above Io's surface in 1979, an observation so unexpected that the imaging scientist Linda Morbido, who first noticed the plumes while conducting routine image processing, initially thought she was looking at a background object. The plumes were Io erupting with a violence and a persistence that no planetary body other than Earth was supposed to be capable of sustaining. Io erupts not occasionally, but continuously. Its surface is resurfaced by volcanic activity at a rate that erases impact craters within a geologically brief time frame. It is essentially a molten world wrapped in a thin crust, squeezed and kneaded by the tidal forces of Jupiter's. Massive gravity and the orbital resonances with the other Galilean moons, Europa and Ganymede Junos, extended mission gave it the opportunity to conduct the most detailed flyby observations of Io since Galileo, and in December 2024 and January 2025, the spacecraft made two extremely close passes of Io, coming within 1,500 kilometers of the surface. The images and infrared data returned from those flybys were described by scientists as jaw-dropping. The GIRAM infrared instrument built by the Italian Space Agency to map thermal emission from the surfaces and atmospheres of the bodies. Juno studied produced maps of Io's South Polar region showing dozens of individual volcanic hotspots, each one a point of elevated temperature indicating active lava flow or fresh volcanic deposits. The number and geographic distribution of hotspots visible in the GIRAM data was higher than previous models of Io's volcanic activity had predicted, suggesting that the total heat output of Io's volcanic system is even greater than the already extraordinary estimates derived from earlier missions. More significantly, the Juno observations allowed scientists to track Io's volcanic activity over multiple close approaches and compare it to previous datasets from Galileo and even Voyager. What they found was a world whose volcanic behavior is not simply constant but dynamic, with patterns of activity that wax and wane at different locations across the surface, individual volcanic centers that appear intensify and quieten over timescales of months, and a global heat budget that remains one of the least well understood in planetary science. The question of where exactly Io's heat comes from, how the tidal dissipation of Jupiter's gravity deposits energy inside Io's mantle, and why that energy is distributed the way it is, rather than concentrating at the poles, as some models predict, is a question that the Juno-Io flybys have sharpened considerably without fully resolving. The latest development, and the one that produced some of the most striking headline results from 2026, concerns what a new University of Chicago and JPL study described as the hidden complexity beneath Jupiter's cloud tops. Published in the Planetary Science Journal in January 2026, the study produced findings that its authors said supported a significantly different model of Jupiter's internal composition than what had previously been assumed. The question at issue was Jupiter's oxygen abundance. How much oxygen exists inside the planet, locked up primarily in water molecules in the deep atmosphere below where Juno's cameras can see. Oxygen abundance is the key to understanding how Jupiter formed a planet that formed close to the Sun, would have incorporated different amounts of water ice than one that formed further out, and the oxygen to hydrogen ratio in Jupiter's atmosphere records that history. Previous analyses of Juno's microwave radiometer data had suggested that Jupiter might be significantly enriched in oxygen compared to the Sun, possibly several times, solar abundance which would have pointed to a formation scenario involving significant accretion of water-rich material from the outer solar system. The new 2026 study, using the most sophisticated coupled chemical kinetic and hydrodynamic model ever applied to this question, found something different. The oxygen abundance is only 1 to 1.5 times solar, not several times solar, modestly supersolar at most, and possibly close to solar. This changes the formation story. A Jupiter with roughly solar oxygen abundance formed from material that was broadly representative of the early solar nebula, rather than from a specific Eichsreich reservoir. As one of the study's co-authors, Jonathan Lunine, a planetary scientist at Cornell University, told Universe Today, the finding provides new constraints on where and how Jupiter formed that weren't available before Juno. The clouds were hiding something. What they were hiding has now been partially decoded, and the answer is telling a new story about the solar system's history. On May 8th, 2025, during its 72nd perijove, Juno made one of its last close passes of Jupiter. The images it sent back of cloud bands twisting into each other at the boundary between zones and belts of storm systems, visible as bright white ovals embedded in darker atmospheric bands of hazes and shadow effects that give the planet the appearance in certain processed images of an abstract painting. In motion were described by the researchers who work with them as still surprising, still revealing things they had not anticipated after nearly a decade of continuous observation. Scott Bolton, the principal investigator of the Juno mission at the Southwest Research Institute in San Antonio, said in a statement that since its first orbit in 2016, Juno has delivered one revelation after another about the inner workings of this massive gas giant. The mission is approaching its end. Juno is planned to make a final atmospheric entry into Jupiter, a controlled plunge into the planet's cloud tops, designed to prevent any possibility of the spacecraft contaminating the Galilean moons with Earth's microbial stowaways at the conclusion of its extended mission. The same fate that ended Galileo's mission to Jupiter in 2003 and Cassini's mission to Saturn in 2017 awaits Juno, a spacecraft that has been circling the solar system's largest planet for nearly a decade, sending back images and data that have required the rewriting of textbooks, will become part of Jupiter itself. What it has given us before that moment is a complete revolution in the way planetary science understands gas giants. A magnetic field that does not look like any magnetic field in the textbooks. An atmosphere that extends hundreds of kilometers deeper than the models predicted. 9 cyclones at the North Pole in an octagonal arrangement that has no analog anywhere in the solar system. A volcanic moon whose heat output and distribution continue to defy quantitative prediction. A water and oxygen content that tells a new story about how the solar system formed 9 years of close observation, more than 70 perijoves, thousands of images sent back from 500 million miles away. And the conclusion that the scientists at JPL and at the Southwest Research Institute and at the University of Chicago, and at every institution working with Juno's data, have been forced to reach again and again with each new dataset, Jupiter is more complicated than expected, more dynamic, more asymmetric, more deep, more strange, more in every direction that science has looked than the models said it should be. The largest planet in the solar system has spent 9 years of scrutiny defying every prediction made about it, and the images it has given back processed by citizen scientists in their homes, rendered in colors designed to reveal structure invisible to the naked eye, printed and displayed and stared at by researchers who have spent their careers trying to understand this world, are some of the most beautiful and most scientifically disturbing objects that a camera has ever captured. Not because they show something impossible, because they show something real, and real turns out to be far stranger than the imagination predicted.